was used to design one of the first convolutional neural networks back in the 1990s. And currently it's used to essentially as a hello world of many applications. But still there are some interesting challenges there. So, number 4 looks like this to us. What computers actually work with is the underlying representation, which is this matrix of numbers. Zeros means it's black, non-zeros is whiter. So you can make out the number 4 right here, because it's a black background. But ultimately, what we feed into a neural network is a set of these numbers, zeros and non-zeros. For example, we can use the ideas from the first few slides and design a neural network that basically takes in the number 4 expressed as its pixels. And here I depicted it as a single vector, but these are completely related concepts. Exactly the same. You can look at the picture as a square, you can look at it as you can flatten it out, you can look at a very long series of numbers. So both representations are essentially the same. And we can fit it through multiple layers, and what we want to arrive at, if you look at the end, is a number, a vector of 10 dimensions with 1, 1, and multiple zeros. And what gives us is a class to which this image belongs. This is so-called one-hot encoding. Where we have 1, it tells us what number this is. So the first would be 0, 1, 2, 3, 4. So it's number 4. So by applying the calculations that we looked at just a few slides ago, what we really want to do is to feed this raw input into the network, keep calculating those new layers and shrinking them. And again, layers don't have to have the same dimensions. You can go from 10 to 20 to 100 to back to 10. And we want to arrive to this final result that would magically tell us what number this is. So one way to do it is to apply a classical, fully connected deep learning network that we know how to design. It's basically a bunch of layers with a bunch of connections. So let's take a look at what it will look like. And as I mentioned earlier, typically networks are represented as linear layers. But we can fold them back into the square layers, because we're talking about images. It's more natural, and consider these to be layers. So, in the first example, we took the input layer, that's incoming image, and the first hidden layer, and we want to calculate the values of the first hidden layer. And the way we'll do it is we will apply weights to every input value and calculate the first output value. Right? That's what we did in the first example, that's what we're doing here. Then we calculate the second value by applying a new set of weights to the input, and we continue until we have our entire hidden layer calculated. It's pretty straightforward, the same formula. So if we do that, and it's only just one layer, but we can stack those one after another, 5, 10, 20, until we get a really big network that can work really well, and we can use it to recognize images. If we do that, let's do some math. So let's say we take a 200 by 200 image. Not a particularly huge image, right? It's a pretty small image. So how many input values will we have? How many? 40,000. All right. So we got 40,000. Now we want to calculate the next layer, which will be again 40,000, right? And I didn't ask the question yet. So what question would have an answer of 1.6 billion?
What are the total number of calculations required for output?
Was it? Right, so how many weights are we going to have between these two layers to go from one to another? And it's 1.6 billion. So we have to store somewhere 1.6 billion numbers, literally in memory, to just calculate this first step. And numbers are typically floats, so how many bytes are in the float?
8. Well, depends if it's long or whether it's short, 32-bit floating point.
So if it's a 30-bit float, how many bytes are in it? Right, so yeah, so a float would be typically 4 bytes, a double would be 8 bytes. So let's stick with float. So 4 bytes, you get 6.4 gig of memory you have to give to just the first layer. So now we want to have a deep network, which is 5 to 10 layers. And now we need 100 gigabytes just to keep these numbers. So by itself, well, I have an example here, 10 layers. That's just half of the problem. Let's say we can build this huge supercomputer and shove it all in. It's still not going to work because the problem is we need to train this network. And we have that many parameters, 16 billion parameters that we need to train. And if you've done any data science at all, right, you know that you need at least, well, not as many, but a reasonable number of samples to train a certain number of parameters. So here we'll need literally billions and billions and billions, hundreds of billions maybe, labeled images to train this mega network. First of all, we don't have that many, and even if we do, it literally will take years and years to train it. So that's why a naive approach using convolutional networks is not going to work too well, because a huge demand for computing power, and it's not even going to work from the computational perspective. Hence, convolutional neural networks. That's why they were designed. Not because people had nothing else to do, but because they had to solve this problem that could not be solved in a sort of a naive way. The first working design is now known as Linnet, and there are different variations. 1, 2, 3, 4, 5 is the most famous one. It is built by Jan LeCun in 1998, and it was used successfully to recognize handwritten digits. His work actually is based on the work of two researchers, neuroscientists, Torsten Hubel and David Wiesel, who experimented on cats in a good way 20, 30 years earlier. So that's what I want to talk about, these experiments. So what they did, they connected sensors to certain parts of the brain of the cats, anesthetized cats, where they hypothesized was the area of the brain of the cortex responsible for visual processing. And then they started showing different dots, pixels, lines, different shapes to the cats. And they were trying to figure out which neurons fire depending on what they show. So what's the correlation between the image that they show and which neurons fire? And I have this video, I hope you will hear, 1 minute video, which describes it really well. I hope you'll hear the sound. What? Is there a volume there? Can you pick? There is some.
No, I think what happened is we're using
No, but it's playing there.
yeah, right here.
When we started working,
Can you turn it up even more? Is it
Can you like find some gate volume button there?
Torsten and I, in the late 50s, we set up our first experiment.
Okay, let me use my microphone.
Stop thinking that.
Okay, I'll do the voiceover. So what they did when they started working on it, well, I've seen this like 25 times, so they started experimenting with these cats and showing different shapes. It didn't actually go that well because they couldn't pick up any signals at all. So they were showing stuff and the cats would just not respond anyway. And then one day they were moving this round circle and they found neurons firing. And when you go find this video on YouTube, you will hear it like crackling sound, like Geiger counter. So that's how they sort of signal that neurons are firing. And at first they thought that was a moving dot, but then they realized that was not the dot, but the edge of that glass plate that they used to actually slide it in. So since it was in the 1960s, they couldn't use computers, so they used this glass plate, and that edge is what actually was triggering the neurons. So that one, oops. So they stumbled this basically by accident. They were about to give up and go work for a hedge fund, but finally they did this final experiment and neurons fired. So, and then in the subsequent videos that are much longer, you can find them on YouTube, they show how they tried hundreds of permutations, moving lines up and down, left and right, diagonally. And what they found is different neurons fired based on really different patterns, sometimes truly bizarre. For example, there was a group of neurons that would fire only when you move the line from left to right, and nothing else. Right to left, up and down. If it's not a line, it would not respond. It would respond to really this weird combination, line from left to right. If you think about it, this is quite amazing because all the neuron cells in the cat's brain and ours, in neocortex, are the same. We do not have a special designed neuron that detects lines, right? We do not have another one that detects movement. They are all the same. So what they found is, despite the fact they're all the same, they can respond to very different stimuli. And the way to do it, there's pretty much only one way to do it, is to have a hierarchical visual cortex. So that was the first, not the first, but the key discovery for which they got the Nobel Prize, is that neurons actually creates layers. And the first layers respond to simpler features. Higher layers respond to more and more complex features. And so eventually, somewhere here at the top, you can have a neuron that responds to this really strange combination of the line moving from left to right and nothing else. So, and that is the idea that went into the convolutional neural network design. There are two core ideas here: hierarchical processing, and the second thing they discovered is that each neuron, or group of neurons, they only respond to a small area of the visual cortex. That will become very important in a couple of slides. Just keep that in mind. So, basically that's a schematical representation how it might work. You go through layers, like we've done before, and lower layers have very simple features. Higher layers go to more and more high level until you can differentiate between arbitrary images. And that's the second thing they discovered is a local receptive fields, is that the neurons only respond to a particular area in the field. So, taking these ideas, we can design a convolutional neural network. So one, it will be hierarchical, and kind of similar to what we've done before. But we know that we cannot naively stack ordinary neural network layers on top of each other, because it's going to be too expensive computationally and not even possible to train. So what we're going to do in the next few slides is we're going to figure out what these layers should be. So the first thing that we get in the fully connected layer is we have all the weights and we calculate the next layer. And we figured out that it's not going to work. Too many weights, we can't never train them. The key transition from this to convolutional neural network is to abandon all the connections that go from the previous layer and instead pick only very few. So instead of looking at all of them, we pick only a small number, in this case 4. In reality, for example, in reality it's more about 5 by 5, 4 by 4, 16 and 25. So now we have only 4 weights and we calculate this output value. That's only half of the trick. The other half of the trick is when we move, so the next cell responds only to these 4 cells and doesn't care about anything else. So that reflects how our visual cortex works. So our neurons only look at a certain area and ignore everything else. In fact, these weights are the same for the entire image. So we went from, well, in this case it would have been 3 by 5, 15, 15 by 15, 225 weights in this particular case. We came down to only 4. And so as we continue to go over this image, it's just going to calculate these values for the next layer. So very similar to what fully connected does, but very different at the same time. And that is what's called convolution. So when you read about convolutions, that's basically what it is. Although it is represented slightly differently, and in most cases it's called a filter. So since you have the same 4 weights, in our case, we can represent them as this matrix of 4 weights, and it slides over the field of view of the image and generates outputs. So since we have a fixed number of weights, now how many connections we have does not depend on the size of an image. If the image is bigger, we're just going to slide over a bigger area, but we're still going to have only 4 ways to train. So we drastically reduced the number of weights that we need to train. And also, what we do here is, because the filter is the same, it's going to discover the same features no matter where they are in the picture, if you think about it, right? So if we have a filter that can discover, let's say, vertical lines, then it's going to discover them everywhere, which makes training much easier, because now your neural network essentially allows objects to move in the picture and it's still going to find that object. Previously, when used the fully connected, it looked at all the weights from the picture going to one cell, and then a brand new set of weights going to another cell. It would never learn such behavior, because weights would change from a cell to a cell instantly. So here's an example. This is the input. It's an example of artificially created pictures. So somebody designed them and ran over the image. This is the input image. If you have the vertical filter, which is basically ones and zeros, it's a slightly bigger filter, what it's going to produce is going to sort of reveal or underline vertical lines. It's going to emphasize them. So, and this image, this output, is going to go to the future layers. So future layers are going to be looking at an image that now has lots of vertical lines, or very few of them, depending on what image you feed. And it's going to do something with it. Horizontal filter will do the same thing and find horizontal lines. So this will help the neural network hypothetically differentiate between images that have lots of vertical lines, images that have horizontal lines, and images that have none of those. That will produce very different output, and it will affect the output of the actual network. So in the neural network, in the real neural network, convolutional neural network, where do you think these weights come from? Who sets them? No, not in the real humans, but in the computer network. So. Exactly. So we don't preset these weights. In fact, when you create a brand new network, you initialize it with some. In theory, you could set everything to 0, but it's not actually a good idea for computational reasons. So instead, we use some randomly distributed weights around between 0 and 1, but basically going to be pure noise. And then we're going to train the neural network, and all these weights will be learned by the neural network as it tries to optimize its output and minimize its error. So eventually it will find some set of weights that lets it recognize an image in the best possible way. So that's the one new concept, in addition to deep learning, to the ordinary neural network, is the convolution. The second one is pooling. And the pooling really does is just shrinks the output by a constant factor. In this, there are different ways to do shrinking, and if you use Photoshop, for example, to rescale your image, it will use some more fancy algorithm for downscaling. But for neural networks, researchers discovered that a simple taken maximum of a neighborhood works extremely well. It's extremely fast and leads to very good results. So, and it's called max pooling. In this case, we have a small window, which this size of this window has nothing to do with the window in the convolution network. They're completely different steps. And pooling, the typical size is 2 by 2. So we take this input, take 2 by 2, it's 6, then they take next square, calculate its maximum, and we shrink by a factor of 4. So after each pooling layer, our image is going to shrink. And the reason why I want to do that is, as we go to higher level features, we also want to reduce our dimension of our output, so eventually we'll arrive to our classifier layer, which has how many outputs for digits? 10. Yes, that's what eventually I want to end up with 10. So we're going to go in with 28 by 28, which is about 700 something, right? Go through a bunch of transformations and end up with only 10 numbers. Most of which, well, all of which should be zeros except for 1, and that 1 will give us a class. So these 3 steps, this one, and fully connected at the end, we'll get to it, will allow us to achieve that. So going back to our design is, well, I put the answers here. So this is Linnet 5 architecture. It's a hierarchical network. We'll starting from the input. First is a convolution. So we're going to learn higher level features. Apply pooling, we're going to shrink it. We're going to treat those new images that are the output of the pooling as a brand new images. We're going to feed it the next stage of convolution pooling stage. Again, it will apply the filter, learn even higher level features, shrink them again, And then 2 or 3, and that's the variable that you will likely experiment with to figure out how many layers work best, or just ordinary connected network at the end to build a classifier. And this is going to be a pretty small set of weights because now we're working with a much smaller input, right? Because we shrink our image by a lot, and we only have a couple of layers to do that. A different way to see it like in parallel is you have here an image as an input, convolutions, they scan these boxes, and then pooling shrinks it, then we repeat the convolution, shrink it even more, and then do fully connected layer. And here they have an example of the image recognition for the categories of images. We would only care about digits, and again, digit 4 is all one recognize. Are there any questions so far?
So you mentioned the first convolution layer. You try to learn the sequence. So if you, let's say the network learned the horizontal one, then you take on the horizontal one. How many convolution layers do we have back to back here in those places? Along everything.
You mean this one?
Yes.
Okay, good catch. So I was talking about a convolution, and I pretended that there is only one. So the good question is actually, if you go back and you would say, well, we have this convolution, but it's only four, or maybe in the real world, 5 by 5, 25 weights. That's not a whole lot. So the network that only has 25 parameters isn't going to do too much. So the way the network is designed is that you now can stack as many as you want. And again, there are, based on experimentation, different network designs have different numbers of these filters. So the net 5 in this first layer has 6. So in other words, you can imagine we have 6 randomly initialized filters, and we apply them independently, one after another, and we generate this stacked 6, not 3, but 6 outputs. And then we basically pass them to the next layer. Those 6 filters are trained independently, and they allow to find up to 6 different types of features. Now, 6 is a pretty small number. It's more than sufficient for a NIST digit data set, for which this network mostly is designed. In fact, it actually can do quite well on some other data sets, and we have a series of workshops coming where we're going to look at things like traffic signs. So it actually works pretty well for traffic signs, and with some slight modifications achieves pretty remarkable accuracy for such a simple network. Now for bigger networks, just one second, this can be 100, 128, 256 layers deep. So big networks have a lot of convolutions that allow you to learn lots of different features and pass them to the layers up. There was another gentleman here with a question. Yeah?
So how do you tell that it's the right answer at each stage? Because with feedback, right?
Right. So, well, let's imagine. So we built a network. We initialized it. It's randomly initialized. We passed in number 4. What are we going to get as an output? Well, so it's going to generate 10 numbers, right? In theory, we want them to be all zeros and on the 1 in the 5th position. But first, we're going to get some random noise. It's going to generate some garbage, right? It's going to have. So all these numbers add up to 1. So this is kind of a very extreme example. In practice, there's a probability that this image belongs to this category. This is a very well-trained network that says, I'm 100% sure it's number 4, which is likely to happen on a simple data set. In reality, it could put like 10% in each and every one of them and saying, I have no idea what this is. So when that happens, there is a formula, a simple formula that calculates the difference. So you can think, we can naively use like Euclidean distance and say, what's the difference between this? It's just not a very good metric. There's a better metric called cross entropy, but it's the same idea. It calculates the loss. And it tells the network you're far off. And this is by how much. And then we use the algorithm called backpropagation and gradient descent. Again, pretty simple formulas. I'm not going to go into them right here. Where we take this difference and we go back layer by layer and we adjust every single weight a little bit. And weights here, fully connected weights. Pooling does not have any parameters. Pooling just shrinks it, so there's nothing to train there. And each convolution has its own set of weights, called filters. So all those things will get slightly adjusted. Then we feed this number back again, we go forward, we get a new answer, hopefully slightly better. Then we plug the difference again and repeat that many, many times. And that's how we get the network that is trained.
Yeah, I'm sorry if I just got lost there, but, so in each convolution, for each set of 4, we have a separate set of 4 parameters, we have the same set of convolution.
Each convolution has one filter, so think about one set of 4 parameters, it's one convolution.
Each convolution layer or each convolution set? That's what I'm.
There are no convolution, well, there's a problem with terminology. So this is we're going from a previous input layer to a convolutional layer. So convolutional layer can have multiple convolutions. Each convolution has its own matrix of weights. So a convolutional layer can have 6 matrices, or it can have 100 of them. Does it make sense?
And in this case, we're trying to say that for your example, there are 5 of them per.
6. There's, well, in this picture it's 3. So I'm going to redraw this picture. It's hard to explain when things don't match in the picture when what I say. So in Limit 5, there are 6 layers. Here they depict on, not layers, sorry, 6 convolutions. Here they depict only 3. So this is a 1 layer. So layers are basically this big part. So this is one convolutional layer. There's 3 in this particular image, 3 convolutions. And then we go to the next layer, which is pooling, which has the same number of sort of slices, because it just operates slice by slice. And we continue.
When you are doing the backward propagation, and then when you are collecting those errors, there are 3 metrics. How do you distribute those gradient?
So the question is, when we're going to do a backpropagation and there are 3 of these layers, how we distribute the error, so it would actually naturally will come out of it. I can't explain it by waving my hands. If you look at the formula, so what essentially will happen is this is a multidimensional input essentially, right? And we do the gradient will have, what the gradient will be, it will have as many dimensions as your layer has. So you think about it as partial derivative, right? It's a 3-dimensional thing, you have 3 partial derivatives. So they will give you an error for each layer automatically.
Layer by layer, I understand, but what you are saying, one convolution is 1 layer.
So, yes, so it's 1 layer, but each layer can have an input as a vector. See what I'm saying? It's not just a number, it's a vector. So you can think about this.
No one explained a vector, some people like not quite understand.
So you can think about this layer as taking in a 3-dimensional number, which essentially a value has 3 values in it. And the first value comes from one slice, the second from the other, and the third from the third, and then you pass this forward. That's considered to be a single value. So everybody knows what a vector is, right?
Yes.
All right, good. So you can think about it as basically a vector, right? At each point. One part of the vector, second, the third, and we pass it forward.
Why is it fully connected back at the end, and why not
10, great question. It's mostly experimentation, so sometimes you have an idea how many layers you need based on the complexity. So we could experiment it a lot, and in the design that I'll show in 1 minute for 3 minutes, actually I tried 3 and 4 and 1 and 2, and then you can see what you do, you add them, and then you run your tests, and you see what the accuracy is. And you can see when the accuracy is increasing, you say, well, that's great, let's add more. But when you add more, the accuracy starts declining. It's counterintuitive slightly, but you say, well, that's too many, so let's go back. So 2 or 3, and you can see both variations, is a reasonable number of connected layers for this network. 10 would be way too many. And the reason why the accuracy will decline is because when you have too many layers, we're going to go back to the problems that we have too many parameters to train. And the network simply doesn't, it fits perfectly our training set. It basically is called overfits. But when you give a test set, it produces a very low test accuracy. So that would your indication you have too many layers. When your training accuracy is really great, everything goes really well. But when you give a test set, the accuracy is really low. So that's overfitting, and you want to start reducing the complexity. And reducing the number of fully many layers is one of them. It's one of the ways. parallel, every part is independent from each other, right? So this is the image, this is the first layer, and it does its own calculation. It produces multiple, what's it called, feature maps. These are not layers, but multiple outputs that we feed into the pooling layer. So,
You mentioned in reality, there's going to be states, well, very strong here on the motion layer, we have 3 filters. It looks like I'm saying the first filter layer stays independent of the second or the third one, because it is fully connected.
yes, well, in fact, the filters are independent from each other. So when you're talking about filters, in this case, a network would have 3 filters, 3 independent sets of 2 by 2, and it can manipulate them independently during learning.
Do you mix them in the
You don't mix them, you just pass forward the output of those filters. Those filters never leave this layer. They are property of this layer. It's a weight that belongs to this first layer. All the filters do is you apply them to the image, produce some output, and then that output is passed to the next layer. That's it. Next layers never get exposed to the parameters of this layer. All they get is the output. And so in a sense, filters belong here, and here you have fully connected a set of weights, which is quadratic between layers. Did that make sense?
I thought the second motion layer has to mix the first layer's filters, like the horizontal plus the vertical, so we can get all kind of shapes.
No, it doesn't touch filters. It only works on the outputs. Now, it's possible to design a network in a very exotic way where that might be the case, so that's the kind of the future. The great part about this particular network is that all the latest, well, most of the latest networks, AlexNet, VGGNet, Google's network, that win this annual image recognition competition, they essentially look like this network, only they're much bigger. They have more layers. Instead of 5, they have like 20. And instead of 3 or 6 convolutions per layer, they have 100 or 128 and so on, and have giant fully connected layers. But once you know how this works, you can pretty much see what the current networks do. So maybe I can show you an example how all of this can be programmed in BigDL. So BigDL is like, I'm going to yell, so I hope you'll hear me out there. So all of this, what I'm going to show you now is so who uses Docker? Who knows what Docker is? Oh, okay, so I have 2 setups. One is a Docker, the other one is for the image. At Amazon. I'll email all of you those setups, and you can use, if you have a Docker installed, you can simply pull my Docker image, start it like I did now, and that's what it's going to pop up. Sorry, what? Are you projecting? Oh, okay. What I did. No wonder. There we go. All right. So there's a Docker image. When you run it, it will have a bunch of files. We go to notebooks. And again, the Docker image runs Spark, runs BigDL library. BigDL library is very easy to install on Spark. This is a developer setup. Of course, you don't run Spark on your laptop to actually benefit from Spark's capabilities, but for development, that's great. And other than that, it's a perfectly production level setup. It runs Jupyter Notebook on top of that. So, and the only difference that you will see, so the Spark.
What is Spark?
That's probably a question for a different.
Cool. Spark is a distributed data processing framework, so you can kind of do Hadoop like MapReduce, but all in memory.
So Spark is a replacement for Hadoop MapReduce. Actually, it's a replacement for Storm, which was a replacement for Hadoop MapReduce. So it's a big data processing framework, which is currently getting Spark allows to do this cool stuff. So SC as a variable that's automatically initialized when you run on Spark, and I just run it to make sure nothing is broken. Unfortunately, nothing is broken. If it works, it will return this object Spark context. So I need my engine. So I have images on my disk that this cell reads. Basically, it reads data from the subfolder and populates train images, train labels, test images, test labels. So these are vectors, basically arrays. So the first one is a training set of 60,000 images that are 28 by 28 size. And I'll show you the actual images in a couple of cells. One means how many dimensions it has at every point, and it's a grayscale image, so there's only one number there, so it's one dimension. Now there are labels associated with that tell what number that actually is. Labels are actual numbers, and there are 60,000 of them. Then we have test set, 10,000 numbers, images, 10,000 labels. So the reason why we need two, what we're going to do, we're going to use training set to train the network. And again, as I mentioned, it's easy to overfit. In other words, if you take a giant network and you pass 60,000 of these simple numbers in it, you might achieve only 100% accuracy. But all it basically tells you is what the network has seen, it almost memorized internally, so it just spits out the known numbers. That's why I have a test set. And once we pass the test set, then the network will make predictions. So when we're going to pass the test set, we're not going to tell the network what the numbers actually are. We'll say, hey, predict now, tell us what you think it is. And we'll take that number and compare it to what we actually have in our initial set of labels. And that will give us the accuracy, how good our network is. If it's 100% accurate, then all numbers will match. So here's an example. I'm printing a random number, and it's still not looking good because I have dimensions. We can do better than that, right? Here. Let's do this. So yeah, it's all kind of wrapped around, but it's the number. So number 8. So the label 8 came from labels. This is the number, and this is what it looks like to humans, right? So what we're going to fit into a network is essentially these matrices with zeros and non-zero grayscale intensities. So let's see how many classes we have. 10. So it's always a good idea to check to make sure we're. In fact, we can see what they are. So classes are just numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. So right. One thing I haven't covered here, and if you come to one of our workshops that we have different meetups every other week. Oh, this Tuesday. Oh, okay, great. Good to know. So this Tuesday in the evening, 4 or 5, we'll send out a notification and an email. One of the promises of deep learning, and there is a site called TensorFlow Playground. It's not TensorFlow, it's just a simulation of a neural network. Is that neural networks, when you do data science using classic algorithms, distributed regression, running forest, and everything else, 99% of the time, or 95% of the time, what it takes is feature engineering. So you have to figure out what the features are, throw away redundant ones, generate new ones, maybe hybrid ones. So that takes most of the time. Once you have features, you fit them into the algorithm, and it produces the output. That part is easy. The promise of neural network, deep learning in neural networks, is that it can feature engineer for us. So we don't need to do any processing. In fact, in this case, as I've been repeating it multiple times, we're going to feed raw pixel data. We're not going to figure out how we should represent this data. We're going to show it to the network and say, you figure out what to do with it. But there is only one transformation we're going to do, and that is normalization. And that's purely computational reasons. Neural networks don't work really well with numbers that's way outside 0 to 1 range. So when you start writing formulas, you'll see that the gradients explode. It will still work, it will just take a lot longer to train. So what normalization does, it takes the picture from 0 to 55 and just scales it from 0 to 1. Well, in fact, in this case, from 0.1 to 0.9. So where we have 255, we have 0.1. Where we have 0, we get 0.1, and now will be in between. Nothing changes. There is nothing
Linear scaling?
linear scaling. It's just the most simplest linear scaling that you see. It's right here. That's all it does, right? To apply exactly the same scaling to every single thing we're going to feed into this network. And that just makes it converge much faster. That's it. That's the only transformation we do. There is nothing to think about here, nothing to figure out. It's just very simple linear scaling. And this is our network design. So if you remember the slide with these layers, it's literally matches one to one. We start with convolution, followed by reloop. That's the nonlinear function. Max pooling, then again convolution pooling again, and then finally we have two linear, two full linear layers, and I have a third one in between. As I mentioned before, you can add one, see what works better, and you can remove one, and experiment with that. So now I built my model. As you can see, the language is very simple. The library has a very simple API. You can create neural networks very, very easily. I'm not going to train for the whole set of all the way through because it will take a few minutes. I'll just say 3 epochs. Who knows what epoch means in deep learning parlance? World data set. So basically we have 60,000 images and we're going to eventually pass them all to the network. A full pass will take a bit of time and that's called epoch. So when we pass the first time, the network will learn quite a bit, but not necessarily everything. So we're going to do it again and again and again until we see that our accuracy kind of leveled out, no longer is changing. At which point we say, whatever we now learn, that's what it's going to be. And that's what the one full pass of the data set. So the optimizer is an object they're going to train our network, and there are multiple training algorithms. Some of you who worked in the morning, the session, saw a slide with different training, SGD, delta, adagram. So here you can choose different ones. I picked SGD with zeros, momentum, so-called. It all doesn't matter if this network is going to train with everything. But that's what basically the algorithm we're going to use to train the network. And here I'm going to specify some visualizations that we're going to use to see what the network does. Okay. Optimize. Oops. Well, this let's go. Well, we're out of time anyway. So, had it worked, we would have trained the network, and then here we apply this model. So all of this is available online. So if you have Docker, your logic is just one Docker pool, you run it, and you have this notebook you can step through it. If you don't have a Docker, you can use an AMI image I will share. So a few more steps. You need to go to Amazon and kind of set it up. You get this very notebook, you get to this step, and you can run a train model on your test set. Remember that's 10,000 units. And we'll produce predictions. At which point we can calculate how accurate our model is, and you can print different letters in what the network thinks they are. So the predictions will be pretty accurate, about 93–94%. So it will take you a while to find the first instance of a mistake, 20–30, right? So maybe you do something more better than random sampling, like I did. And then you can see when the network makes mistakes, why, what the image looks like, and maybe it makes sense to make a mistake in this case, or maybe not. And then you can experiment with fully connected layers here, or any other layers, and see if you can change the accuracy. So all of this is pretty much self-explanatory. You can add an extra line and rerun this calculation. So,
The magic URL.
that
Magic URL.
the magic URL again.
So